To start.
Hello students. Now I am going to discuss the one experiment of your syllabus, that is determination of wavelength of laser by diffraction grating. Now what is, first of all you have to know what is diffraction. So diffraction is basically, suppose this is a small open portion, okay. Now suppose a light falls on this and dimension of this obstacle and the wavelength of this light is comparable, suppose. Then from this knife edge the light will bend towards this geometrical shadow region. So this is basically the diffraction, definition of diffraction. Now, so you can see grating. What is grating? So this is one picture of grating. Now there are two types of grating. One is transmission grating, another is reflection grating. Now what is transmission grating? So take one example. Suppose you have one small glass plate, and how can one can draw something on a glass plate? So you take one diamond knife edge, and you draw some line on the glass plate. So where you draw by the diamond knife edge, that portion becomes opaque, and the rest portion remains the transparent. Now if light falls on this, so suppose this is the transparent region and this is the opaque region. So light will not pass through, and the picture is something like this. So if I place it like this, so this is the opaque region and this is the transparent region. Now if light falls on it, it will bend, and the dimension of this open portion is very small, almost comparable to the wavelength of laser light or whatever light you are using. Now this is a picture how basically diffraction is happening. So suppose some light is fall on this lens, and what is the use of this lens? It makes the light parallel to the grating plate. Now the light will bend, then you place another lens and it will place all the light on this screen, and you can see this type of diffraction pattern. Now when we go to the setup, experimental setup, you will see that there is no such type of lens. So why there is no lens? Now here the light is laser basically. Now you know laser is very much collimated beam, and the width of this laser light is very small. That is almost parallel. Now there is no need to do the parallelization of this laser light. Okay, so that's why there is no lens is used here. Now, so coming back here, you have to know what is this basically. This is the grating. I have told that this is the transmission grating. One example of transmission grating. When you draw something on a glass plate, it becomes transmission grating. And one example of reflection grating is your laptop screen. So there are so many pixels, and if light falls, and you can see diffraction pattern. Okay, so forget about that. We are going to discuss about this transmission grating. Now, here this is the, I told this is the opaque region and this is the transparent region. So this transparent region will be treated as a slit. Okay. Now suppose the width of this slit is A, and the width of this opaque region is B. So A plus B if you do, it becomes another parameter, that is D. So this D is called grating element or grating constant or pitch of grating. So this D is constant for a particular grating. Okay, this D is constant for a particular grating. Now how you measure this D? So this D is, so you can see this D is basically the distance between these consecutive slits. If I show like this is the distance between two consecutive slits. Now, how can you measure? So, when I will show you one grating, you can see there some number is written. That is, suppose 100 lines per millimeter. So, in 1 millimeter, there are 100 lines. So, these are all rulings or lines on the grating. So, in 1 millimeter, there are 100 lines. So, in 1 centimeter, there will be 1000 lines. So, suppose there are n number of rulings in 1 centimeter. Okay, so how many slits will be there in 1 centimeter? There will be n minus 1 number of slits. Now D will be 1 by that n minus 1. So in this case, there will be 1000 lines in 1 centimeter. So D will be 1 by 999 centimeter. So that you have to use to measure the lambda of your laser. Now the basic working formula is D sin theta equal to m lambda. So the underlying theory you will read in your theory class. So let me give you some basic information about this. So here what type of diffraction is happening? There are two types of diffraction. One is Fraunhofer diffraction, another is Fresnel's diffraction. So here Fraunhofer diffraction is happening. Okay, Fraunhofer diffraction is happening. And here this condition is for interference maxima. So whatever pattern you are seeing, so in the screen you will see some dot in intensity of light, That means this is the central interference maxima, this is the first order interference maxima, this is the second order, this is the third order, like this. So both sides you will see some dot on the screen. So that position, so here this theta is, suppose the light is bending like this and this is theta 1. So this will be theta 2 from here, from the central spot. So that's theta 1, theta 2, theta 3 we have to measure. So D you know, if you measure theta 1, theta 2, theta 3 like this for different m. So what is m? For first order m equal to 1, for second order this is 2, for third order this is 3. So you have to put m accordingly, and you can measure lambda for different order, and you take average. Now let me tell you the experimental setup, some idea here, then we will go to the setup and you will see the setup. So whatever measurement we will do on spectrometer. Okay, so in the spectrometer, in one side there will be the laser source. So laser will come out from here, and grating will be placed on the revolving plate. So that there is the circular scale is there, and you will place your grating so that you can move. Now this is the detector, so light will fall, and if light is fall directly on the detector, you will get more value if the intensity is higher. So in this way you can measure the position of those interference maximas. Now, so this is that circular scale. Now if I show it here, this is something like this. So there are two openings, two parts. So this is vernier 1 we will tell, and this is vernier 2. So in the vernier 1 you can see there is one main scale, and above which there is the vernier scale. Now in vernier scale there are 60 division which will match with 59 main scale division that I have written here. And in the main scale, the smallest division you will see 1 by 3 degree, means, so in 1 degree there will be 3 divisions. So suppose this is 179 and this is 180, there will be 3 divisions. So in so the smallest division will be 1 by 3 degree. Now the vernier constant for this circular scale will be 1 main scale division minus 1 vernier division, and if you put it here it becomes 1 by 180 degree. And now how you will measure the thetas? So in that case, so you have to measure the main scale reading. Then you have to check one of the vernier line will match with one of the main scale line. So that vernier line count you have to measure. So suppose that is vernier. Now with this vernier reading, suppose the vernier 50th vernier line is matching. So with that you have to multiply the vernier constant, and it will give you the total circular scale reading 1 theta you will get. So in this way, for different AM you have to find out this total circular scale reading, and you have to put on this formula, and you can find out the unknown lambda. Okay. So this is the experimental setup. So this is called the spectrometer. Now this part is basically one collimator was there, and that actually is removed, and one laser source is put here, and this is the telescope, and where this detector is put in. Now, and this is this grating. Now as laser light is falling on this grating, you can see that there is the pattern is coming. So suppose this is the so this will be the central spot, and here you can see there are two vernier 1 and vernier 2, and you can see the main scale and vernier scale. So for this position you have to measure vernier 1 and vernier 2 both. Okay, so this will give you the central spot. Now this was the central spot. Now this is the first order, this is the second order, third order. So what you have to do, this is the detector, and so this is the central spot. Now you have to move this detector like this, and it will be the first order. And here this, when this light is falling on this detector, there is one transducer which is converting this light energy to electrical energy. You can see that if I go in between, the light voltage becoming low. Okay, so when you can see the light is falling on this detector, voltage becoming high. Okay, so in this way you have to place the detector on different positions on the spot, and you have to find out this theta and theta 1. Okay, thank you.